you. Thanks for the introduction, and thanks to the audience for being here. It's an honor to give a talk in this meeting, and my talk will explain what's happening in the global flood awareness system in the next release. I would like to stress that I'm here to present on behalf of a large number of colleagues, both of the European Commission Joint Research Center and at ECMWF. So let's start with a very quick overview about GloFAS. You heard it mentioned also this morning. So GloFAS is the Global Flood Awareness System, and it's one of the components of the Copernicus Emergency Management Service. It provides information on both upcoming and ongoing flood events for all the world, and it is complementary to national and regional services. And it's specifically important for large transnational river basins. Over the years, it has been used by international organizations in decision-making and also to prepare in view of upcoming very big flood events. In this slide, in a nutshell, we see how GloFAS works. So we take the input, the meteorological forecast from ECMWF, and this is the input to the hydrological model, which in the existing operational version has daily time step and 0.1 degrees resolution, roughly 10 kilometers at the equator. The hydrological model provides river discharge forecasts, which are then compared to pre-computed flood threshold to provide the alarms, the points that we see popping up in the GloFAS web interface. The hydrological model is also used to produce the input to an inundation model, to produce flood extent maps, and also to provide a rapid risk assessment layer. The system has been fully operational since 2018, and it is in constant evolution. You heard this morning a presentation about the newest layer, the newest product, the global flood monitoring. But this presentation is about what is going to happen to the core of GloFAS, that is to the setup of the hydrological model. If we want to use just one number, one figure to say what's happening with GloFAS Next, we can say that we can use the number 0.05 because the spatial resolution of GloFAS will increase from 0.1 degrees to 0.05 degrees. That is roughly 5 kilometers at the equator, meaning that in 1 pixel of the existing implementation of GloFAS, we can fit 4 pixels of the GloFAS Next. So the first question is, what are the expected benefits of such a big upgrade? Well, the first one, I think that we can all guess it, because with a higher spatial resolution, we can actually have a better representation of the spatial variability of the catchment's properties in terms of morphology, land cover, soil properties, and so on. But this is, as we can see in this slide, just one side of the story, because the other side of the story is that the existing GloFAS implementation is based on a setup that was prepared in around 2010. But now we can benefit of 10 plus years of research, technological development, and data collection in order to prepare all the input layers that are required by the hydrological model and achieve a better representation of the catchment's properties. So the hypothesis is that if we have a more accurate representation of the catchment's properties, then we have a more accurate representation of rainfall from and eventually we get a more accurate modeling of and forecast of river flow, but also all the other states, such as soil moisture. So now we are probably convinced that this is a great update, but how do we get there? We had to complete 3 main tasks. First of all, as I mentioned, we need to prepare all the input layers, all the maps that provide the feature, the characteristic of the catchments at high resolution. Now we have to run the hydrological model, which now has to account for many more pixels, 4 times pixel, meaning that the hydrological model itself has to be computationally efficient. The hydrological model is LeastFlood open source, and it is a semi-distributed physically based model. And a lot of work has been done to improve its computational efficiency. Finally, when we have the setup, we need to go through a new calibration. So these three steps will be discussed very briefly in this presentation, starting from the maps that are required to implement the model. There are over 100 maps to provide the information on catchments morphology, land cover, land use, soil properties, water demand for human purposes. I'm not going through all the 100 maps. I want just to provide a couple of examples to stress the kind of data that we use to prepare these maps. The first example is the map that shows the evolution over the year of the leaf area index. And this map was derived using a Copernicus remote sensing derived database. While for the soil maps, we actually relied on soil grids, which is a database of over 230,000 soil profiles collected all over the globe. So this is an in situ database. The documentation for each map is available online, and we are also working on a scientific publication. As soon as this is done, we will make the 0.05 degrees dataset fully available for the users to explore it and use it. The model, the hydrological model, as I said, is LeafSplat open source. It is the same model used in the previous version of GloFAS. It is a semi-distributed physically based model where we have 6 land cover fraction per pixel, 3 soil layers, 2 groundwater storages. We use the kinematic wave to model the routing, and we also model lakes, dams, and the water use for human purposes. A lot of work has been done to increase the computational efficiencies, especially for looking at the management of large inputs and in terms of parallel computations, which we implement in both the routing and in the modeling of the water infiltration into the soil. The code is open source, available from GitHub, and we also provide a user guide and a documentation. So now we have our model set up with a semi-distributed physically based model and more accurate input maps. But still, we have to remember that every model is an approximate representation of reality. So we need to implement the calibration to tune the parameters in order to improve the model capability to represent local processes. In this calibration, we decided to calibrate 14 parameters. As we can see in this slide on the left, with all the green circles, I just wanted to stress that we try to calibrate all the parameters that intervene in the most important processes modeled by LeafSplat in order to improve the accuracy of the model. In terms of calibration, well, there are several protocols and several strategies. The protocol that we implemented for GloFAS Next is based on in situ observation of discharge measurements. And for this purpose, it is important, and this cannot be done without an extensive database of observation of discharge. In the map that we see here in the bottom right, the blue area represents all the catchments for which we have discharge measurements within our database. So for those catchments, we can actually implement the calibration using discharge data. And then there are all the yellow areas for which we don't have discharge measurements. And for these areas, we will have to implement another strategy. So we had to implement a complementary strategy for the calibration. We can start first with the, let's say, most straightforward one for the catchments where we have discharge measurements. In this map, we see all the points where we have discharge measurements. The difference in color is it means to stress how many catchments, how many calibration points we were able to add compared to the previous version of GloFAS. So in black, we have all the calibration points that were already included in the previous calibration in the GloFAS, which is now operational. But in orange, we see all the calibration points that were added over the last 2-3 years. This is partially because with a higher resolution, we can actually calibrate smaller catchments, so we can include more calibration points. And then, of course, over the years, there has been a big effort to include more points, more discharge observation in the database. In terms of technicalities, the algorithm that has been used to calibrate the model is the distributed evolutionary algorithm for Python, and the KGE is the objective function that has been selected. The calibration algorithm, the calibration tool, is open source, and it's available again from GitHub. And now we can move on to the results of the calibration. So in this map, we see all the calibration points and all the results of the calibrations. The color bar is the KG, which is an index that we use to evaluate the accuracy of the model. The best possible value is 1. The model has skill if we start from 0.41, minus 0.41 to 1. So the points for which the model has skill go from pink to yellow to green and to blue. We can see in the map that we have a fairly good distribution of yellow, green, and blue points, but still we have some points that pop up in black for which we still need to do some improvement. But if we compare this map with the same color bar to the map representing the performance of the existing operational model, which is visible in this slide, we can see that the new implementation of GloFAS provides a large improvement. And in the next slide, we see basically the same piece of information, but in a lumped manner. So this graph that we see here is the empirical cumulative distribution function of the KG values. Ideally, we would like to have the performance of our model very close to the green line on the right. In the black, we have the performance of the existing 0.1 degree implementation. In red, we have the performance of the GloFAS Next. So we can see that there has been a shift towards the right with an improvement on model accuracy. But we have to remember that so far, we spoke only about gauge catchments, so catchments for which we could do the calibration using discharge data. So all the blue areas. The yellow areas are still to be analyzed. For these yellow areas, we decided to implement a pragmatic regionalization approach. By pragmatic, we mean that it had to be, let's say, simple enough, but still scientifically based, to be implemented within the timeline of the operational release of GloFAS Next. This is because as soon as we have an improvement to the system, we want to make it available to our users. While, of course, in the background, we will keep on working and maybe implement some more sophisticated calibration. But for the pragmatic regionalization approach, based on a literature review, we decided to use the transfer of the complete parameter set from a donor calibrated catchment to a target uncalibrated catchment. So here in this map, we see in black all the donor catchments, which are all head catchments. And the question was, now, let's say that we have an uncalibrated catchment here in China. How do we select the donor? We pick the closest, we pick the most similar according to what? So we did an experiment, and we looked at geographical proximity, so if the catchments were close, and also physical similarity. And the similarity was assessed based on climate, morphology, and geology. To establish how to identify the donors, we did a leave one out cross-validation experiment with 739 catchments. In this graph, we see again the empirical cumulative distribution function of the KG. Our target is the green line. The black line is the results for when we actually do the calibration. The red line is our lower boundary. LeaseFlood, as any other hydrological model, comes with a set of standard parameters. So the standard parameters are usually implemented when we don't know any better. This means that if our target with the regionalization was to get a line somewhere in between the lower boundary and the upper boundary. And we did our cross-validation experiment using the different methods to identify the donors. And we were quite pleased to see that all the lines are actually in between the two boundaries. So the regionalization provides an improvement compared to using the standard parameters. And the best criteria that was selected was based on geographic proximity and climate similarity. So now we are at the stage where we completed our mosaic, because we did the calibration using in situ measurements of discharge for the blue area. And then we did a pragmatic regionalization approach for the yellow area. And we are doing during the last few months, we started working on the pragmatic task that will lead to the pre-operational release in Q4 of GloFAS Next, with all the forecasts available from the Copernicus data store. And we will have 3 months of overlap between the existing operational version and GloFAS Next to allow our user to get used to the new version of GloFAS. And we are also working to update the inundation maps using the new river discharge, time series. So GloFAS Next will be likely be called GloFAS 4.0, and we are working hard to make it available by the end of the year. In the meantime, while working at GloFAS Next, we already had several ideas on how to improve further the system. So we already have a bunch of ideas in the background. For instance, we would like to improve, to add more lakes and dams to our setup. We would like to work on the list flat code itself, so changing the routing and also updating the modeling of the reservoirs. And for the calibration itself, there are ideas already about using machine learning or multi-objective calibration, including remote sensing observation. But this will be after we make GloFAS 4 fully operational. And that's it.
Thank you, Stefania. That's really exciting to see GloFAS Next. Are there any questions? I see. I will come up to you. So hold on.
Stefania, can you hear me?
Yes.
Perfect. Thank you for the presentation. Couple of questions. What is the data source for your observation or evaluation of your model? This discharge observation that you use. What is the source for that?
I understood that it's a question about the discharge observation, but I'm missing the keywords of the question.
The data source that you have 1900 cages that you use to calibrate and evaluate your model. What is the data source for that?
Okay, it's actually a combination. It's a database compiled from many other databases. So it comes from the global database already available.
Maybe GRDC?
Yes, correct. Sorry, I was missing the word. Yes, exactly that one. Plus, we have also like users that are happy and are willing to share the data. Now it comes to my mind Semaden from Brazil. And actually in the GloFAS wiki that we make available online, there is a link where all the users can actually get in touch with the team in order to share the data for their own station and request the reporting points. So it's a combined database from database already available, I mean freely available, and then also the data that are shared by the users.